Okay, third section of forces and motion. This is where we bring together the information we have on forces, what we've learned about forces, and all the learning we did in chapter 9, all the Suvat equations. So we're linking together forces and acceleration, and we're using this key formula. Force is mass measured in kilograms times acceleration measured in meters per second squared. And if we look at the units quickly, mass is in kilograms, acceleration is meters per second squared. So force is measured in kilogram meters per second squared. Thankfully, we don't use that unit. We call this a Newton. So 1 Newton is the force required to make an object of 1 kilogram accelerate at 1 meter per second squared. So that's 1 Newton. 1 Newton is 1 kilogram meter per second squared. So all our forces will be in newtons. If your units for mass or acceleration are different to kilograms and meters per second squared, I would strongly recommend you convert them to these two and then do your calculations. So all your force units will therefore be in newtons. Okay, let's have a look at this diagram. It's a standard forces diagram. We've got our forces shown in arrows. There's the object. The object measures 2 kilograms, so the force downwards is 2 times g. G is acceleration due to gravity, as you've seen already. So we often write the force due to gravity as multiples of g. Sometimes we do, sometimes we don't. I've got a new arrow here. This is acceleration. It's invariably written as a double-headed arrow, or drawn as a double-headed arrow, separate from the main diagram. And the acceleration of this particular object is 2 meters per second squared. And what we've got to find here is the magnitude of these two forces. Well, we're given that the object is moving to the right. So the resultant forces vertically are 0, which means that the force due to gravity must be the same as the normal reaction. So y has to equal 2g. Now, as it's accelerating at 2 meters per second squared and the object weighs 2 kilograms, just to remind you, I'll write it in here, the force required to make this object accelerate at 2 meters per second squared, F equals ma. The force required is 2 kilograms times 2 meters per second squared, which is 4 newtons. So the resultant force has to be 4 newtons. We've got a 4 Newton braking force pulling backwards. So the resultant of these two must be 4 newtons to the right, because it's accelerating to the right. Therefore x has to be 4 newtons more than this. So x has to be 8 newtons. In these diagrams, make sure you've got all the forces written on. The force arrows are fixed. They join to the object. The acceleration arrow is separate. That's a double-headed arrow. Okay, let's have a look at one of the examples. We're going to have a look at example 7. It's very wordy, but as I read it, I will add to my diagram the values in the question. So a body of mass 5 kilograms. So this has a mass of 5 kilogram. Therefore, its weight, the force due to gravity, which we call weight, is 5g. It's pulled along a rough horizontal table. A rough table has friction, so we're going to have a frictional force moving backwards. It's pulled along a rough horizontal table by a horizontal force of magnitude 20 newtons against a constant friction force of magnitude 4. It says a constant friction force. You'll find out later that force due to friction can change. So given that the body is initially at rest, our first job is to find the acceleration of the body. Let's label that up. Well, F equals ma, we know that, but first we have to work out how much of this force, this horizontal force, is actually making it accelerate. The resultant force is the pulling force, take away the frictional force. You'll often see forces written like this with little suffixes here. This is the resultant force, this is the pulling force, this is the frictional force. So the resultant force is 20 newtons that way, take away the frictional force. So we actually have 16 newtons pulling this object to the right. Now going back to our F equals ma, so we know that we have 16 newtons resultant force pulling it. It's a mass of 5 times by a. We can therefore work out that the acceleration is going to be 16 over 5, which is 3.2 meters per second squared. Whoops, didn't leave enough space. So that's what our diagram should look like, and those are the kind of calculations that you need. I'm going to do one more question from exercise 10C. This is question 10. It's a question that a few of my students found quite tricky. So exercise 10C, question 10. It says a trolley of mass 50 kilograms is pulled from rest in a straight line along a horizontal path by means of a horizontal rope attached to its front end. Well, we better do a diagram as ever. So trolley of mass 50. I'm just going to show my trolley as a block. If you want to get artistic and put wheels and things on it, feel free. So a trolley of mass 50 kilograms, so it's 50 kilograms, which means we have downwards force due to gravity of 50 g, and as it's accelerating to the right, we must have an equal and opposite normal force, which we'll call r, so r must also be 50 g. It's pulled from rest in a straight line along a horizontal path by means of a horizontal rope attached to its front end. There's the horizontal rope. The trolley accelerates at a constant rate, and after 2 seconds its speed is 1 meter per second. So go back to what we did in chapter 9. Let's write down the information that we might have. The initial velocity is 0. Its final velocity after 2 seconds is 1 meter per second. As it moves, the trolley experiences a resistance to motion of magnitude 20 newtons. So we have the pulling force that way, and we have a force due to friction here of 20 newtons. First we have to find the acceleration, so that's what we want to find. And we're not too worried about the distance travelled for this particular part of the question. Okay, so accelerates at a constant rate, so a is constant, that's what we want to find. We want an equation that links t, v, u and a in order to work out what the acceleration is. V, U, A, T, I'm going to use V equals U plus AT. Some students like to rearrange first and then put the values in. I shall do it the other way around. 1 equals 0 plus 2A. A is therefore equal to half a metre per second squared. So I now know the acceleration. Now I know the acceleration of this object, I can work out what force is required to make a 50 kilogram weight, mass rather, accelerate at half meters per second by using F equals ma. So the force is what I want to work out. This will be a resultant force, of course. It's 50 times by a half. So the resultant force is 25 newtons. So the pulling force is, the resultant force is the pulling force take away the frictional force. So the resultant force, the resultant force, which is 25, because that's the actual final force that we have. That's the pulling force take away the friction. So the pulling force must be 45 newtons. That means that the force this way is 45 newtons. The second part of the question asks, what is the tension in the rope? Tension in a rope is simply the force that is being pulled using the rope. And so the tension in the rope is 45 newtons.